if you apply a voltage between the tip and the sample, you can make the electrons go from the tip into the sample. Or you can reverse it the other way around, the electrons can go from the sample into the tip. So you're basically injecting what's called holes into the sample. If you scan the STM chip across the sample, you can get a nice atomic resolution trace. And the reason for this is because we're basically looking at a one-dimensional tunneling problem. So this is the potential of the sample and this is the potential of the tip. There's a potential barrier between the two because of the vacuum between the tip and the sample, and the electrons tunnel exponentially between the tip and the sample. And this is basically really important. So this is what the tunneling current will look like. And the only thing we need to worry about here is the exponential dependence on the distance between the tip and the sample Z. So on this distance here. This basically means that if we were to bring the tip approximately 0.1 nanometer close to the sample, the tunneling current is going to jump up by an order of magnitude. So this is what gives us the atomic resolution. And along the x and y, so in plane with the sample, we get atomic resolution because the tip terminates in one individual atom. And this is quite important. So when the STM was invented, it won the Nobel Prize in 1996, and these Binnig and Brora, together with I think the IBM football team, but I'm not quite sure. I think they were at IBM at that point. So this is the day when the Nobel Prize award was announced, and they're each holding bouquets. So then they asked Binnig, so okay, so you've got this really nice tool, you can now see individual atoms and surfaces. So what's next? What are you going to do with it? So he said, we're going to play soccer with the atoms. And he was right. So a few years after, this is what followed. That's the IBM logo, written in 35 xenon atoms that were taken individually, picked up with the STM tip, and moved one by one to form the IBM logo. So these are individual atoms. After this, they made the quantum the Corral Stadium, and basically you can see standing waves on the metal surface, so that's iron on copper. Yeah, that's probably a bit too much detail. And recently, this movie came out, the world's smallest movie. I don't know if you might have seen it or not. If you Google it, it's one of the first things to come up on YouTube. So this little boy basically plays around with matter, and it's actually made by individual atoms moved around one by one. So what's common between all of these is that they're all made on metal surfaces. What I work on is basically the same thing, atomic manipulation, but on semiconductors. So I'm currently working with silicon. So this is the silicon surface. Each bright spot is an individual atom, and you can't quite see the length scale, but this is just 2 nanometers plus. And the silicon unit cell is shown in red. It involves 12 silicon atoms. This is an image taken with positive bias, so we're tunneling weak electrons from the tip into the sample. If we reverse the bias to negative bias, that's what the surface will look like. So you can just about see that one half is brighter than the other, and this is because because of the way that the silicon surface reconstructs. So it's actually quite a complicated arrangement, and I'm just briefly going to go through it. So the bright half is called the folded half, the dark half is called the unfolded half, and they have completely different electronic properties, which is what we look into, what we explore and test. So this is what the silicon surface reconstruction is actually like. So it has 4 different layers to it. So the silicon surface actually comprises 4 layers of add atoms. And what we see is just the add atoms on the top layer. So these ones here. And the reason why these ones look bright is because there's a stacking fault on this half, and that's the dark dots in between the add atoms. Another important location on the surface is right in between these atoms, which I can't quite hold my hand, sorry. So in between them we have the rest atoms, which are in yellow and green here. And they look dark. And the reason for this is that there's 3 electronic states into which our electrons can tunnel into on top of the add atoms, and that's why they look bright. but on top of the rest atoms, which are in between the other atoms, there's no free electronic states, which is why they look dark at the voltage we're at in the thermal interval. So what we do is we take the silicon surface and we put some molecules on it. And these dark spots on our silicon surface are actually molecules. If we increase the scanning bias, the bias at which we're scanning at, so we're now using high energy electrons, or high-ish, we're still in a few eV range, so they're not actually really high. So yeah, if we increase the tunneling bias and scan over again, these molecules are going to leave the surface, they're going to dissolve. And what my supervisor noticed a few years ago was that if he did this experiment, so that's an image taken after he has done the experiment, all the molecules have left the surface. If you scan outside the surface, you can see that quite a few other molecules have left the surface. And this is non-local, this is the so-called non-local atomic manipulation. So essentially, the tip has only been in this area here, but a lot of molecules over here have also been affected by what the electrons have done. So this means that we now have a tool which allows us to probe what the electronic transport on the silicon, only in the silicon surface layer, is like. So this is one experiment that I've been working on. So what we do now is we dose our surface with a lot of molecules, we inject in the middle, and we see that a lot of molecules far away from the injection site have left the surface. And what I was actually going to focus on is what I've been working on most recently, like over the last half a year or so, which is trying to differentiate between what happens right underneath the STM tip, so right just to the molecule that's right underneath the STM tip, so not with all these. So we're not worrying about where the electrons go, just how are we coupling into the silicon surface. And what we've done is we've been able to automate everything. I have a nice video to show that. So what we do is we allow you to start an experiment. You can't really see it there, unfortunately. We scan the surface. We then send the information back to MATLAB. MATLAB finds all the locations of the silicon atoms and the silicon molecules. So it can pick at random which molecules we want to do something with. So essentially we can help, basically it does our experiments for us. And the reason why we want to do this is because we're in quantum mechanical in the regime of quantum mechanics, so everything is probabilistic. So to get really nice statistics, you need to do this hundreds of times. And in any other lab, doing one of these experiments is probably going to take the whole of somebody's PhD. So essentially we do this, we find all the molecules, we position the STM tip on top of them, we inject electrons and record the height and the current trace and check whether the electron has left the surface or stayed. And I'm going to skip the rest of this video. So the information that we get from this is we've recorded the time and current and the height of the STM tip, and essentially this tells us when the molecule has left the surface. So we know exactly how many electrons we have injected into that molecule before it has left the surface. Doing this a lot of times gives us a nice solution to a first-order rate equation. So essentially each one of these spots is an individual molecule that we have manipulated. It has left the surface and the measured time, which is related to the number of electrons that we get. And it is really nice to an exponential. And this basically tells us whereabouts local manipulation starts taking place. And you can just about see that there's a threshold that starts kicking in around here. So these are the electronic states of the sample and the molecule. And you can see that there's an onset in the electronic states of the sample. So essentially what it's telling us is that we don't worry, it's only the sample that ever does anything it is set up, which contradicts everything else that people have known so far. So people thought that the electrons go into the molecule, excited, it vibrates, leaves the surface. Instead, the molecule is a complete bystander, and the silicon surface is extremely reactive. So I have a few more results to show you, but I think I'll have to skip through them. Just wanted to thank you for listening, and thank my research group and the University of Bath and the SSIC for coming. Thank you.
Most interesting. Now I do understand the title, which is great. So, some questions? I'm sure there are many.
We got one. Can you use
the microphone?
Can you actually use that technology to study dislocation formation in stainless steels or austenitic steels?
I guess so, but only on the surface. So we're only looking at the surface. So I don't really know what dislocation is. What is this?
It's just a sort of a lack of atoms in the atomic structure.
Yeah.
Just like you showed with the silicon.
Yeah. So all you need to have is just a conductive surface, and it needs to be flat. So we look just at the surface, we can't look at the bottom.
More questions?
Could this method actually be used on biological membranes, for example? Will it disrupt them somehow?
It wouldn't disrupt them because the electrons we're using are very low energy. So it's very different from scanning electron microscopy where you have 20 kiloelectron volt energies. Here you're just a few electron volts. It's just down to are they conducting or not. So can the electrons go and see them? Yeah.
And it can influence whole molecules, not just...
Yeah.
Okay, so if, say, a protein, which is like a giant molecule, can influence the whole molecule?
It can do, yeah, so if you tunnel into it, so it depends what substrate you're going to use. So the molecule itself might not be conductive because it's on substrate, it's going to saturate diamond bonds and whatnot, I'm not a chemist. And yeah, you can inject into it, you can manipulate it. People have made atomic molecular switches, so bistable molecules and surfaces, you inject into the molecule, the electrons affect the whole orientation of the molecule, or yeah, completely change it. It flips between two bistable sites, and that gives you an atomic switch.
Does this satisfy the requirement to be flat surface? Because the surface of membrane would be necessarily flat.
Yeah, it depends how big it is. Again, like quite flat with a few nanometers here. So the correlation here is maybe half nanometer. I've scanned different things, so it depends how much resolution you want out of it. In there, you can have a few nanometers reference. It will still work.
Questions? I'm just wondering, in order to get the scale, so you say that you can manipulate, let's say, a single atom, and apparently that influences a whole area around that atom as well. So what is the size in maybe the size, in units of size of atoms that these correlations actually are?
There's absolutely no upper limit. So we've tried really big sizes, so we usually look at images that are 10 nanometers, say, but we've gone up to 100 and we still see it happening, and it's not being affected by grain boundaries, so it doesn't matter how the surface conforms, and it's not being affected by steps either. What's interesting is that the transport mechanism is actually diffusive on silicon, which is a completely new thing. People thought it was going to be ballistic. But instead we find a nice diffusive transport, and it fits a better equation, which is quite good.
Okay, more questions? Well, if we have no more questions, then let's thank you.